In this lecture, we are going to discuss forecasting, which will lead us into our next coding example. This lecture will focus on how to do a correct forecast because, unfortunately, a lot of resources do this in a way that makes your results look really nice but actually make 0 sense. So first, what does it mean to forecast? In the way that we mean in this course, it means that we have a time series, and our job is to predict the next values of this time series. Importantly, notice that I used the plural there. We want to predict multiple values, not just one value. The length of time that you want to predict is called the horizon. In some applications, your horizon might be 3 days or 5 days. For example, if you're trying to predict the demand for each product at a factory, you might want to forecast the demand over the next 3 to 5 days. Another pretty obvious example is the weather. Let's say we want to predict the hourly weather over the next 7 days or so. So if we predict the weather for each hour over 7 days, that's 7 times 24, which is 168 hours. So if your sequence step size is hours, that would be predicting 168 steps ahead. This is important, so remember, you don't want to just predict one step ahead. As a side note, forecasting is a huge topic. You could study an entire book about forecasting. This course is not that. We're just touching on specific points which are relevant to deep learning and RNNs. Now you might recognize that this section is all about RNNs, recurrent neural networks. So where are the RNNs? Well, we are not there yet. A common approach in machine learning, especially in the industry, is to do the simplest thing possible. Don't throw an RNN at a problem if there is a simpler method available. So my question for you now is, what is the simplest way to do a forecast given a single, one-dimensional time series? Well, how about we go back to our approach at the very beginning of this course, linear regression. Linear regression is in fact one of the best models to use to study forecasting because it's very intuitive and there's not that much going on in terms of formulas and manipulating equations. At this point, you might raise an objection. If our data is of shape n by t by d, we can't use linear regression because linear regression works on 2D rectangles of shape n by d. And if you were thinking this, that's a great sign. That means you're thinking about shapes, which is exactly what you should be doing. So how can we reconcile this apparent contradiction? Well, in fact, linear regression does only work on data of shape n by d. But remember that, in our example, we are considering only one-dimensional time series, so d equals 1. As you know, this is just a superfluous dimension. We can represent the exact same data in a two-dimensional array of shape n by t. Again, this is analogous to the situation where you have an n-length one-dimensional array, or you can have the same array stored in a two-dimensional n by 1 object. So how do we use linear regression in this situation? The answer is, we pretend that t is d. Or to put that a different way, in this scenario, linear regression treats t as if it were d. This is another instance of my rule, all data is the same. Let's think about how our data will look. Let's suppose we have a time series of length 10, and we want to train a model to predict the next value in the time series using the past 3 time steps. In this case, our input matrix will be of size n by 3, and our target vector will be of size n. Now, what is n? As mentioned previously, we can calculate n as the number of length 3 windows that fit into the time series, which is length 10. So that's 10 minus 3 plus 1, which is 8. But wait, remember that we would like to be able to predict the next value, which is the target. So while we can fit 8 windows into the time series, we can't actually use the last window in our training set because we don't know the next value. Suppose our data is just x1, x2, all the way up to x10. In this case, if our input is x8, x9, and x10, we can't have x11 as a target because we don't have x11 in our time series. So in actuality, we only have n equals 7. So really it's like asking, how many windows of length 4 fit into the time series of length 10? That's 10 minus 4 plus 1, which is 7. And this is because the fourth value is the target. So what does a linear regression forecasting model look like? At this point, it should be pretty clear. It's x hat at time t equal to w0 plus w1 times x at time t minus 1 plus w2 times x at t minus 2 plus w3 times x at t minus 3. While I'm using time indices here, you should still be able to recognize this as linear regression. As a side note, this is called an autoregressive or AR model in statistics nomenclature. The word auto means self, so it's a model that tries to predict the value in a time series using its own values. Okay, so using this model, how do we forecast? Here's a common thing I see a lot. Let's say our test set consists of the data x11 up to x20, and we want to calculate the test accuracy on our test set. So you might say, take the data matrix that we see here, x8, x9, x10, x9, x10, x11, and so on, and plug that into model.predict. Then we'll get the predictions for x11, x12, x13, and so on. Unfortunately, this is wrong. As a side note, please be aware that models in PyTorch do not have a predict function. We're just using this notation for convenience, since it allows us to express how to make the model predictions using one line of code. You should recognize this notation from scikit-learn, so you can just frame this lecture in the context of using a scikit-learn model rather than PyTorch. So why is it wrong? Remember that we would like to use our forecasting model to predict multiple steps ahead. What we just saw was only predicting one step ahead. This is not good enough. Let's say we want to predict 3 days ahead. We want to use day 1, day 2, day 3 to predict day 4, day 5, and day 6. What were we doing before? We used day 1, day 2, and day 3 to predict day 4. That's fine. Then we used day 2, day 3, and day 4 to predict day 5. That's not fine. Because remember, we don't know the value on day 4 yet. Today is only day 3. Similarly, we can't use day 3, day 4, and day 5 to predict day 6. So what do we do instead? If we want to make predictions multiple steps into the future, we must use our own earlier predictions as input. For example, in order to predict x5, we use x2, x3, and x hat 4. X hat 4 was calculated from x1, x2, and x3. To predict x6, we use x3, x hat 4, and x hat 5. This is the correct way to forecast. Now, note that this doesn't mean one step ahead predictions aren't useful. It just means you have to know when to use and when not to use them. Because we have to make predictions sequentially, we can't do it all in one call of model.predict like we did before. Instead, we need to use a loop and call model.predict only on the most recently generated sequence. In this pseudocode, I'll attempt to express the main idea. Our first sequence x, we initialize to the last values of the train set from which we want to predict the first value of the test set. We also initialize an empty list to store our predictions. Then we enter a loop that goes for the number of steps we want to forecast. Inside the loop, we call model.predict to get only the next immediate value. We store this in our predictions list. Then, and this is the important part, we discard the oldest value in x, and we concatenate the rest of x with the new prediction. We assign that to x. Then, when we call model.predict on the next round, we are using an x that contains both true values and predictions for the forecasted values. As a final note in this lecture, I want to think about how can we apply the rule all machine learning interfaces are the same in order to build a more powerful predictor. One limitation of linear regression is that the prediction can only be a linear function of its inputs. Luckily, we already know how to build a more powerful model that works on the same kind of data, an ANN. So by being an expert in deep learning, you can immediately apply this technique without any extra effort. That's a pretty powerful approach. All of a sudden, you are able to convert your classic statistical time series forecasting model into a modern, superpowered nonlinear neural network forecaster. And that's all just with one line of code. Not bad.